All right, good morning, everyone. This is classwork number 20 in week 8, and we're going to be looking at independence. So the objective is for students to be able to determine whether two events are independent or not independent by using two-way tables. And we'll specifically be looking at conditional probability. So make sure you've done classwork 19 before you do classwork 20. Okay, so let's get into first example. Recall the hypothetical 1000 two-way frequency table that we used in classwork 19 to classify students at Rufus King High School according to gender and whether or not they participated in an after-school athletics program. So we filled this table out ourselves in the last lesson. Again, make sure you did 19 before doing 20. And now we're going to look at how this relates to independence. Okay, so number 1 says, for each of the following, indicate whether the probability described is one that can be calculated using the values in Table 1. Also indicate whether or not this is a conditional probability. Okay, so remember, conditional probability means given that an event B has already occurred. Okay, so part A says the probability that a randomly selected student participates in an after-school athletics program. So we want to know two things. Can we calculate this value, and is it conditional? So if we see randomly selected student, I'm going to say this is not conditional because we're looking at the whole population. There's no condition. There's no event that we need to already happen. So this is not conditional. And can we calculate it using the values in Table 1? Randomly selected student participates in an after-school athletics program? Yes. And we're going to calculate this in the next part. Okay. Number B, or part B, the probability that a randomly selected student who is female participates in an after-school athletics program. So I'm emphasized who is female because that would be a condition, okay? The event that has already occurred is we've already picked a female student. We know it's going to be female. That event has already occurred. So that means that this probability is conditional. And can we calculate this probability using our table? We're going to see, okay, is female and participates in an athletics program on the table? Yes. Part C, the probability that a randomly selected student who is male participates in an after-school athletics program. Who is male? That's our condition. So this is conditional. And is that value in the table? Male and participates? Yes. Okay, so now that we've done part 1, part 2 is going to be to actually calculate these probabilities. Okay, so use Table 1 to calculate the probabilities. They're the same ones that we just did. The probability that a randomly selected student participates in an after-school athletics program. That's going to be not conditional, so it's going to have a denominator of the entire population, which is 1,000. And we're looking at any student who participates in an after-school athletics program. So that's the total. We're going to go 400, which equals 0.40. If this looks familiar, it is because we did this in classwork 19, but it's going to come into play again, so it's important that we go over it. Okay, part B is the probability that a randomly selected student who is female participates in an after-school athletics program. So if we know the condition is female, that means our total is going to be the total number of female students, and that will be our denominator. And then participates in an after-school program and is female will be 232. So that's the number of students who are female and participate in athletics, divided by the total number of students who are female. And we get 0.40. That's the probability. We're not going to write the percentages because they're asking for probability. Okay, and C is the probability that a randomly selected student who is male participates in an after-school athletics program. So male given that they're male, that's going to be our total. Total number of males is our denominator. And then we want to know the males that participate in after-school athletics, which is 168. And we know that probability is going to be 0.40, or you can, check that in the calculator. Okay, so part 3 asks, would your prediction of whether or not a student participates in an after-school athletics program change if you knew the gender of the student? Explain your answer. Take a second to think about that. Pause the video and hypothesize something. Okay, so hopefully you have an answer. And if we're predicting whether or not a student participates in athletics, we're really looking at what's the likelihood or what's the probability that that student plays a sport or participates in athletics. So I would say no. The gender has no effect on whether or not a student participates in athletics based on those probabilities, right? Because we see, for athletics, we see 40% of students who are female participate in athletics, 40% of students who are male participate in athletics. So the gender is not affecting who participate in athletics, right? So my prediction would not change. I would say, okay, the whole school, 40% of students play athletics. That prediction is not changing at all based on the conditional probabilities. So this leads us to our definition of independence. Two events are independent if knowing that one event has occurred does not change the probability that another event has occurred. Okay? So we're talking about a conditional probability here. Knowing that something's already happened. That's a conditional probability. If we know that a student's female, that doesn't change the probability that they play a sport. Okay? So that's the example, right? If F is the event that a randomly selected student is female, and S is the event that a randomly selected student participates in an after-school athletics program, events F and S would be independent if the probability of that a randomly selected student participates in an after-school athletics program is equal to the probability that a randomly selected student who is female participates in an after-school athletics program. So, knowing that a randomly selected student is female does not change the probability that the selected student participates in an after-school athletics program. So these two events are independent, okay? So the probability that a randomly selected student is female matches the probability that a randomly selected student participates in after-school athletics, okay? So we have these two probabilities that are the same. Okay? So let's go to an example where we're going to have not independent. Okay? So these two probabilities were equal. So gender and probability that somebody plays a sport are independent in this case. All right. Example number 2. Consider the following data. We've worked with this data before as well. The asthma versus somebody in the household smokes. Okay? This was some students in Wisconsin or something. So number 1 says, you are asked to determine if the two events, a randomly selected student has asthma and a randomly selected student has a household member who smokes, are independent. What probabilities could you calculate to answer this question? Okay, pause the video, try to brainstorm 2 probabilities. Okay, so remember, for independence, we are comparing with a probability of out of the whole sample compared to a conditional probability, okay? So we want one conditional probability and one non-conditional. And one conditional, at least, to compare these. So for a non-conditional probability, if we're looking at a randomly selected student has asthma and a randomly selected student has a household member who smokes are independent, we're looking for has asthma and somebody who smokes. This is the data point that's most in question. So we want to compare, given that a randomly selected student has a household member who smokes with a randomly selected student has asthma. Okay? And then one of these has to be conditional. So there's a couple different ways to mix this up, and I'm just going to give you one example. So one non-conditional would be, okay, what's the probability that a student has asthma? So that's 182 divided by 937, because that's asthma out of the whole population, which is going to be, let me grab my calculator, 182 divided by 937, which is 0.19. Okay, so we know about 19% of students have asthma, not dependent, or we don't know if that has any correlation with whether someone has smoke in their house smokes. Okay, now we're going to do conditional. So what if we say, okay, what's the probability that a student has asthma given that somebody in their house smokes? So we're going to say a student who has asthma, given that somebody in their household smokes. We're going to go with somebody in the household smokes in the denominator, and the student has asthma and has somebody in the household who smokes as the numerator. And we get 113 divided by 395 equals 0.28. So we're comparing two events, right? Two probabilities. The probability that a randomly selected student has asthma with the probability that a student who has asthma, this is randomly selected student. That's randomly selected student with asthma. That's our first one. Our second probability is given smoking in-house. Does student have asthma? Okay. So if I were to use these two probabilities, I could answer this question. The probability that a randomly selected student has asthma, and given smoking, that a student has asthma. Okay? So, let's look at question number 3. Is the probability that a randomly selected student who has asthma and who has a household member who smokes the same as or different from the probability that a randomly selected student who does not have asthma but does have a household member who smokes? Okay, it's a long question. We can do it. Is the probability that a randomly selected student who has asthma and who has a household member who smokes the same or different from the probability that a randomly selected student who does not have asthma but does have a household member who smokes? Explain your answer. So we can calculate these probabilities and find it out, or you can use your intuition. Now I'm going to calculate them, okay? So the probability who has asthma and who has a household member who smokes out of a randomly selected student is going to be taken from the probability of someone who has asthma and has a household member who smokes. That's our 113 out of our total 937. And we know this value. Oh, we don't know this value. We're going to calculate that value as 113 divided by 937 is 0.12. And we're going to compare this with the probability that a randomly selected student who does not have asthma but does have a household member who smokes. So we've got does not have asthma and does have a household member who smokes out of randomly selected students. Okay, so that's going to be 282 divided by all students because it's a randomly selected student. There's no condition here. And we get 0.30. Okay, so the question is, Are these the same or different? So we're going to say the probabilities are different based on our calculations from the two-way table. Oops, okay. So these probabilities are different based on calculations from the two-way table. Finally, a student is selected at random. The selected student indicates that he has a household member who smokes. What is the probability that the selected student has asthma? Okay, so this is a student is selected random. They indicate that they have a household member who smokes. That's our condition. So we know we're going out of household members who smokes, which is 395, and we know that they have asthma. No, we don't know that they have asthma. We're looking at what's the probability that they have asthma, which will be looking at students who have asthma and at least one household member who smokes, which is our 113 number. And when we divide that, we get 0.28 as the probability that, given somebody already smokes, that our person gets asthma. Okay? So, what we've got is, since these two probabilities are different, we cannot claim independence, okay? All the probabilities we've calculated have given us pretty different answers, right? So we talked about our percentage out of the whole here and our percentage out of the given here, or these probabilities are different. And then again, we did probabilities with randomly selected students who do not have asthma out of students who have a household who does smoke, and those probabilities were different, and we get a different probability here. So all in all, we cannot claim independence. Now, we cannot say they're dependent, right? We would need an actual scientific study to claim dependence, but we can claim not independent. We can't say dependent, but we can say not independent. There is a difference between that. And if you're still confused, definitely shoot me a text or come to my office hours, okay? And just to summarize this lesson, this is the whole point here. We can organize data in two-way frequency tables that can be used to calculate conditional probabilities, right? We've been doing that for a couple lessons now. Two events are independent if knowing that one event has occurred does not change the probability that a second event has occurred. Okay? So this is where we're comparing a conditional probability with a regular probability. And finally, probabilities calculated from two-way frequency tables can be used to determine if two events are independent or not independent. Okay? We are never going to say dependent. We're just going to say not independent. All right, let me know when you have questions. Talk to you later.